This station, in cooperation with the Atomic Energy Commission's Argonne National Laboratory, presents Atomic Year 25, a silver anniversary documentary on the birth of the atomic era. Producer for this radio special is Ed Ronnie of Argonne's information staff. Mr. Ronnie.
An event that changed the course of man's life occurred on December 2nd, 1942, at the University of Chicago's Stagg Field. Scientists achieved a nuclear chain reaction. Matter had been changed into energy in a dramatic transformation. No other event has revolutionized both war and peace in such an impressive way. The atom, a potential as we know for war, but also for man's good, for use in exploring space, combating diseases, and providing power for home and industry. Here then is the story of the world's best-kept wartime secret, as we look back on it from Atomic Year 25. The atomic age was not born overnight. There was talk of nuclear power in the early 30s. Dr. Emilio Segre, now at the University of California at Berkeley, experimented with radiation in those early days in Italy.
This feeling that one had to quit atomic physics and go on to the nucleus was much stronger, and we started to do something about it. This was in the years 1931, 32, 33. Well, remember that in 32, then there were the great discoveries: neutron, heavy hydrogen, deuterium, the positron. I mean, it was very clear that our feelings were correct, namely that the nucleus was going to become the great thing.
Niels Bohr, a brilliant Danish physicist, arrived in the United States in January 1939. He was deeply concerned about the implications of a recent experiment by Otto Hahn and Fritz Strassmann at the Kaiser Wilhelm Institute in Berlin. Bohr's colleagues, Lisa Meitner and Otto Frisch, had told him of this experiment before he left Europe. Hahn and Strassmann had produced fission. Neutrons had entered a nucleus, split the atom, and released energy. Bohr met Albert Einstein at Princeton, New Jersey, and told him about the discovery. From there, the news reached men like Dr. Enrico Fermi and Dr. Herbert Anderson at Columbia University. Dr. Fermi, an Italian-born Nobel Prize winner, had come to this country about the same time as Bohr. Dr. Anderson was a member of Fermi's team at Columbia. He now is at the University of Chicago. He tells of a meeting of scientists towards the end of January of '39.
Very shortly after my initial meeting with Bohr and then Fermi, there was a meeting scheduled in Washington in theoretical physics. And with Bohr's news, the interest and attention of the meeting immediately focused on the new development. And the meeting heard speeches by Bohr and then by Fermi, who outlined what they understood about the process and its significance. Of course, this sent various scientists running to the laboratory to confirm the result, and excited the news reporters very much when they began to sense the wide implications that this new development might have for the world.
In February 1940, the first government funds were set aside for investigating the possibilities of making an atomic bomb. Secret experiments got underway at many university campuses. At the University of California, in December 1940, a group of chemists discovered a new element, its given name, plutonium. Dr. Glenn Seaborg, now chairman of the Atomic Energy Commission, was a co-discoverer of this element.
Well, the significance of plutonium for the war effort was, of course, its use as the explosive ingredient in the nuclear weapon. Plutonium also, of course, has a tremendous potential for peaceful uses. It is the fissionable isotope that is produced from the abundant uranium isotope, uranium-238.
November 1941. Scientists concerned with the project concluded that, in theory, a pile of graphite and uranium could be assembled so as to support a chain reaction, and in this process a portion of the uranium would be converted to fissionable plutonium, and that the plutonium in turn could be used in a weapon. The late Dr. Arthur Compton, a much-respected physicist at the University of Chicago, was to become the director of the Pile Project. He later became president of Washington University in St. Louis. In a recording made 15 years ago, Dr. Compton comments on a high-level meeting in Washington on December 6, 1941.
We discussed the enormous difficulties involved in making an atomic chain reaction, which was as yet only an idea on paper, of learning the chemistry of plutonium, and of developing a method for separating it from the other substances in the presence of the lethal radiation of tremendous intensity. We agreed that though it was difficult, it wasn't impossible. Thus, as an afterthought, I was commissioned to bring together the physicists who would endeavor to set up the chain reaction, and the chemists who would look for a method of extracting the plutonium after it was produced. That was on Saturday. Sunday, the following day, I learned of the Japanese attack on Pearl Harbor. The nation was alert. Our project became more vital to us than life or death. From all parts of the country, men competent in the field rallied to give what help they could. The University of Chicago campus was made the center of the effort to produce plutonium.
Dr. Norman Hilberry, today at the University of Arizona, was made associate director of the project. He knew he had a job to do, and the problems were enormous.
It was fairly clear that the real problem in establishing a chain reaction was the absorption of the neutrons produced in fission, the absorption by impurities. It was nip and tuck as to whether or not one would be able to get a chain reaction with just normal uranium and any sort of moderator that we could lay our hands on. Consequently, we took a hard look at what the purity of our materials were, and the impurities present were just spectacular in their nature. They could swallow up neutrons like nobody's business. Now, there were two areas in which we simply had to get rid of these impurities. One of these was in the uranium. Now, that was half of it. The other half was the graphite in which you embedded this uranium also had to be pure because the neutrons went wandering around all through it. That was what it was there for. And if there were impurities in it, then you were in trouble.
Dr. Leona Libby, now at the University of Colorado, was the only woman scientist on the project.
Now, Wally Soon wouldn't let me work at the squash court because, you see, everybody wore overalls and goggles and a mask against the dust, so everyone looked alike, and a miner's cap, a regular striped blue ticking workman's cap, so everyone looked alike. And he said in case he had to say nasty words to somebody, he didn't want it to be a girl. So I was excluded from the actual construction, although I was in and out every day with calibrations and measuring the growing neutron flux of the reactor as it added layer by layer.
Dr. Seaborg and several of his colleagues moved their laboratory to Chicago in the spring of 1942.
Actually, I came to Chicago at that time with Dr. Isidore Perlman, and I left Berkeley on April 17, 1942, on the City of San Francisco streamliner, and arrived in Chicago on the morning of April 19th, which happened to be my 30th birthday.
The scientists came, men like Eugene Wigner, Frank Spedding, Samuel Allison, Leo Szilard, Walter Zinn, and many others. a select group working hand in hand on one of the nation's most urgent projects. And in those hands, the unknown power of the atom, soon to be unleashed. June 1942. A once top-secret letter stated, "Laboratory evidence is convincing that a suitable structure of pure uranium and graphite should result in a chain reaction which would become self-sustaining if enough material were used." August 1942. Dr. Seaborg and his team of chemists were able to see plutonium for the first time. It had been produced in a cyclotron.
We first saw, and this represents the work of Burris B. Cunningham and Lewis Werner, plutonium in the pure state on August 18th. And it was first weighed in pure form on an ultra-micro balance on September 10th.
Also in August of 1942, the U.S. Army engineers were now taking charge of the bomb work, and the entire venture was given the code name Manhattan Project. Leslie R. Groves was promoted to a brigadier general and placed in charge. He describes the circumstances at Chicago at that time.
It was essentially the transition period between the college laboratory type of work and industrial research. And it was just in that in-between stage, and it was in that stage when I first saw the Chicago affair.
After building up, testing, and tearing down more than 30 different piles, in late November 1942, the final configuration of materials was beginning to take shape. Crews worked around the clock to piece together 385 tons of pure graphite, 40 tons of uranium oxide, and 6 tons of uranium metal. It was decided that an airtight cover should be available for the pile. Dr. Anderson sent an unusual order to the Goodyear Company. "We need a huge square balloon."
Well, needless to say, a square balloon was something unheard of by the Goodyear Company. They'd made balloons in all kinds of shapes, but always round. But there was a war going on by this time, and they were beginning to get used to strange requests. Although they were very much mystified, they quite willingly cooperated and turned out to be very helpful and produced a very good square balloon.
Early December would be the time for verifying all the painstaking calculations, and hopefully, we were ahead of the Nazis. On the morning of December 2nd, it appeared to some scientists on the plutonium production work that the project might be on shaky ground. A reviewing committee of leading engineers met with Dr. Compton in Chicago. They were looking into a number of ways to make fissionable materials. The committee had been charged with recommending to the government how to proceed with the atomic bomb project. 2 weeks earlier, they had concluded that 500,000 man-years of effort would be required, and they felt that it might well prove to be an impossible task. On recording, the late Dr. Compton recalls that meeting.
The reviewing committee met me in the conference room. "Where's Fermi?" they asked me. Enrico Fermi, 8 years before, working in his laboratory at Rome with the help of a single assistant, had shown how to handle the neutrons that play the vital role in the nuclear reaction. He was now directing the construction of our experimental atomic reactor. "I'm sorry," I replied, "but Fermi is asked to be excused. He's busy in the laboratory this morning. Perhaps I can answer your questions." And so we discussed back and forth for several hours. The telephone rang. It was word from the research team. "We're ready to try the critical experiment." I chose the youngest member of this reviewing committee because I thought he would have a longer time to remember what he had seen. And so I took with me Crawford Greenewalt of the DuPont Company, and we walked over to the laboratory. We entered the balcony at one end of the room. On the balcony, a dozen scientists were watching the instruments and handling the controls. Across the room was a large cubical pile of graphite and uranium blocks, in which we hoped the atomic chain reaction would develop. Inserted into openings in this pile of blocks were control and safety rods. After a few preliminary tests, Fermi gave the order to withdraw the control rod another foot. We knew that that was going to be the real test. The Geiger counters registering the neutrons from the reactor began to click faster and faster till their sound became a rattle. Throw in the safety rods came Fermi's order, and you could see the pointer move right back to zero. The rattle of the counters fell to a slow series of clicks. For the first time, atomic power had been released. It had been controlled and stopped.
That was Dr. Compton. Crawford Greenewalt, now chairman of the board of the DuPont Company, comments on his reaction on that day.
Well, the scene wasn't very exciting. Actually, people were very calm. I think there was a general confidence in Fermi and a general confidence in the fact that the pile would go critical as planned. And so there was no gnashing of teeth or tearing of hair or anything of that sort. It was very calm.
Among the others who were present on that cold December afternoon, 3:25 p.m. to be exact, was Dr. Walter Zinn, today a vice president of combustion engineering.
Well, for people who were deeply involved in it, it had to be a little bit of an anticlimax. And the reason for saying that is that what happened on December 2nd was not, so to speak, a sudden surprise to anybody who was involved in it. Because as we built this structure, we made measurements continuously which told us that we were approaching the chain reaction situation.
Dr. Compton topped off the activities of the day by phoning Dr. James Conant. Dr. Conant was the chairman of the National Defense Research Committee. Dr. Compton, again on recording, tells about that closely guarded telephone message.
As the reviewing committee left, I picked up the phone and called Dr. Conant at Cambridge. He knew of the critical experiment on which we were engaged, but he hadn't expected results quite so soon. We talked as usual, in an extemporaneous wartime code. The Italian navigator has just landed in the New World, I told him. The Earth was not as big as he had supposed. What I had in mind was that the uranium and graphite pile didn't have to be made as big as had been anticipated. So he arrived a few days earlier than he had expected. Were the natives friendly? Was Conant's response. Everyone landed safe and happy. Such was the birth of atomic power.
Confirmation of the chain reaction studies with the CP1, Chicago Pile No. 1, was an inspiration and reassurance to scientists on the project. General Groves, viewing the plutonium work from a military standpoint, provided this objective statement.
I wasn't particularly elated because I felt that it was just one of the steps that had to be overcome. My job was very definite, been assigned by Secretary Stimson, which was a very definite mission, was to bring the war to an end sooner than it would otherwise end, and thus save American lives by the development of atomic energy. And each step was like one rung up the ladder, and there was an awfully long ladder.
Dr. Seaborg continued his research with plutonium.
Actually, the process for the production of the plutonium, as it involved the chemical extraction process, was not even conceived until after the success of CP1. We immediately then went forward at as fast a pace as possible to develop this chemical extraction process.
Someone had calculated that it would have taken 70,000 years for the CP-1 pile to produce enough plutonium for one bomb. Without a doubt, it was necessary now to proceed with full-scale production plants. The Chicago story, told here only fleetingly, was only a part of the overall Manhattan Project. As General Groves stated, it was one rung up a long ladder. There were more than 70 research groups under Dr. Compton scattered around the country. Even before the Chicago pile succeeded, a large atomic pile was being planned for Oak Ridge, Tennessee, and the design for those at Hanford, Washington, followed swiftly on the heels of this event. The mammoth plants at Oak Ridge and Hanford were to supply the raw materials, like uranium-235 and plutonium, for the weapons work at Los Alamos, New Mexico. At sunrise on July 16, 1945, the sleeping desert near Alamogordo, New Mexico, was illuminated by the light of 1,000 suns, and the sound of the atom torn asunder reminded one of doomsday. It was the first test of a nuclear explosion. Dr. Segre was right in his prediction of 1932. The nucleus was to become a great thing. Japan surrendered. Peace had come, and with the new era, a new tool, as important for its peaceful uses as for defense.
What really has happened has been that by adding to our raw materials certain quantities of artificially radioactive materials, we are now in the position in which we can make inanimate objects communicate intelligently with other inanimate objects. For example, we can make a piece of paper, tell the machine that is making it whether it's doing it right or not, and if it isn't doing it right, tell the machine how to correct what it's doing so that it will be right. Now, this is just one example. There are just loads of others.
The whole Mojave Desert could be turned into a garden using a desalinization plant run by nuclear energy. And it would set an example for the whole world.
The development of atomic energy as a source of power has opened up a replacement which is exceedingly abundant, perhaps much more abundant than fossil fuels ever were, so that mankind will have the energy to do his tasks for many years, perhaps many hundreds of years more, than if atomic energy had not been discovered.
President Lyndon B. Johnson, speaking on atomic energy, said this about the future of the atom.
This energy is to propel the machines of progress, to light our cities and our towns, to fire our factories, to provide new sources of fresh water, and to really help us solve the mysteries of outer space as it brightens our life on this planet. We have moved far to tame for peaceful uses the mighty forces unloosed when this atom was split, and we have only just begun.
This station, in cooperation with the Atomic Energy Commission's Argonne National Laboratory, has presented Atomic Year 25. Producer and narrator has been Ed Roney of Argonne's information staff. This has been a special broadcast commemorating the 25th anniversary of the successful achievement of a controlled nuclear chain reaction at the University of Chicago on December 2nd, 1942.
Atomic Year 25 is coming soon over this station. The special documentary will tell the story of the birth of the atomic age. I'll be your host for the special. I'm Ed Ronnie. Do listen for Atomic Year 25. This station will present Atomic Year 25, a silver anniversary documentary depicting the birth of the atomic age. The historic event took place at the University of Chicago on December 2nd, 1942. The once top-secret events that took place at the University of Chicago on December 2nd, 1942, will be described in a special documentary over this station. I'm Ed Ronnie, your producer and narrator for Atomic Year 25, a silver anniversary special produced by Argonne National Laboratory. Listen for the dramatic story of the world's first controlled nuclear chain reaction. You'll hear the actual voices of the scientists who took part in the historic event. This is Ed Ronnie. I'm the producer and narrator for a special documentary that soon will be carried by this station. We invite you to listen for Atomic Year 25, a 25-minute special which commemorates the silver anniversary of the birth of the atomic age. It all took place at the University of Chicago on December 2nd, 1942. You'll hear the actual voices of the leading scientists on the project, their thoughts and recollections. You won't want to miss it. Coming soon over this station.